Alright, hello, welcome to our Math 2413 weekly review. This week we are going to be covering linear approximation, differentials, and absolute extrema. So first let's go ahead and get started. Alright, so the first thing we're going to cover is section 3.10, which is going to be our linear approximation differentials. So let's say that we have a function that looks a little something like this. Now let's say at some point A, we have our tangent line. All right. So we have that point, but now let's go ahead, like I said, we have some function. This is our function f of x. And then this is our tangent line at a f of a. Now let's go ahead and zoom in a little bit further on this drawing. Let's go ahead and zoom in a little closer to that point, a f of a. All right, once again, we're kind of crossing around down here and going back up. And once again, here we are at our point A. And then we've got our little tangent line going like this. If we look close, we can see that if we are, let's say we travel anywhere along this at just some general point, x, we can see that the distance between x and our function really isn't that far as long as we're relatively close to our initial point A. Now, granted, if we start moving further along, we can see how they become further away. But once again, this is actually a very, very close distance whenever whenever our tangent line is close to our point A. That can actually let us approximate what our value on our initial function f of x is from our tangent line. So let's say we have some point B that we're wanting to figure out on f of x. If we know f of a, but we can't really figure out f of b, like an exact value for f of b, then we can actually just, because this distance is so close between a and b, we can use our tangent line from f of a to approximate f of b. And that method is going to be called linear approximation, and also known as tangent line approximation. So in an algebraic sense, linear approximation is the idea that we can approximate f of x as being f of a plus the slope of the tangent line of f of a times x minus a. And this applies when x is close to a. Now let's go ahead. So now that we know this can actually bring us to a similar idea called linearization. And this is essentially turning this into a hard function, saying that once again, we can use what the linear approximation or the linearization is exactly equal to f of a plus f prime of a times x minus a. So essentially, linear approximation is the concept and linearization is just the exact number we're going to get spit out whenever we plug things in, whenever we use our linear approximation. So, and once again, linearization just kind of gives us another general form where we can plug in different values of x. So now let's go ahead and try to do a couple examples with this concept. In this example, we want to find the linearization of the function e to the x minus 1 at a equals 1. Use this to approximate e to the 0.85, e to the 1.2, e squared, and e to the negative 4. Right, so let's go ahead and think about what we'd use for our linearization equation. Once again, general form is going to be all of that. Our linearization is equal to our initial y value plus the slope of our tangent line at our plus the slope of our tangent line at a times the difference between x and a. So let's go ahead and see what we have. We know a is 1 and f of x is going to be e to the x minus 1. So let's plug in f of 1, and that's going to get us e to the x minus 1 over e to the 1 minus 1, which is equal to e to the 0, which is equal to 1. Now let's go ahead and find our derivative and our derivative point at point A. So once again, we need to find f prime of x of e to the x minus 1. So if we derive e to the x minus 1, we're going to be left with, of course, our initial exponent function. And using our chain rule, it would be times the derivative of our exponent. So derivative of x minus 1 is just 1. So therefore, our derivative is once again e to the x minus 1. Now we can go ahead and plug in our f prime of 1, which is once again e gives us e to the 1 minus 1, which is e to the 0, which is 1. Now let's plug this into our linearization equation. So we know that our general L of x is equal to our f of a, which is 1, plus our f prime of a, which is once again 1, times x minus our a, which is 1. This gives us 1 plus x minus 1, which simplifies down to just x as our linearization equation. So now it's time to go ahead and plug everything in. So now we're going to approximate. So now let's start off with approximating e to the 0.85. So L 0.85 would just be 0.85. Because our value is just x, whatever we're going to spit in is going to get spit back out. So we can essentially just go ahead and create a table. So now let's go ahead and make a table with our x. And our L of x. So we have 0.85, 1.2, 2, and negative 4. If we plug in, so once again, our L of x just spits the same thing back out. Now let's look at something else. Now let's look at something a little interesting. I want to let us see if, just kind of see how these values change as we move away from A. So let's go ahead and do our x minus A, an absolute value. So if we take 1 minus, so if we do 0.85 minus 1, that is going to get us negative 0.15, but we're taking the absolute value, so that is 0.15. 1.2 minus 1 is just 0.2. 2 minus 1 is just 1. And negative 4 minus 1 is negative 5, but the absolute value gives us 5. Now, let's go ahead and look at another interesting thing. I want us to take a look at what happens when we find the absolute value of the difference between these. Between our actual value and our approximation. So let's go ahead and look. And just to make things a little easier, I'm going to go ahead and make a separate, add a little last column just with our f of x, just so we can actually see what we're looking at. So I've already went ahead and plugged all these into a calculator for our f of x values, and we can compare these in just a second. So if we plug in 0.85 directly into our function, so if we go ahead and look exactly at 0.85 minus 1 for e to the 0.15, we're going to get 0.8607. Then let's see, f of 1.2 is going to be 0.2. 1.2214. The next value is going to be 2.7183. And lastly, we're going to get 6.739 times 10 to the negative 3. All right, now let's look at our difference. So if we take 0.8607 minus 0.85, we are going to be left with 0.0107. If we take 1.2214 minus 1.2, we are going to be left with 0.0214. If we plug in, then for that next one, if we take 2.1783 minus minus 1, we're going to get minus 2, we're going to get 0.7183. And lastly, if we take the difference between our f of x and our L of x, this one's going to get us, take the absolute value, we are getting 4.0067. These values can show that, once again, show that as we move further and further away from our point A, our approximation becomes much worse. Because we can look really closely at like this 0.85 and 1.2 and see those are very close. 2 isn't even that far off. The issue becomes like, but however, if we move all the way from like negative 4, which is 5 units over, we are nowhere near close to our initial value was. But But let's say we want to actually go ahead and make sure we have an accurate value. Let's say that we want to go ahead and yield a certain accuracy. Well, there's actually a way we can do that. What we can do is we can restrict our approximation to a certain accuracy. When we do this, we're going to use a certain form. So we're going to have the absolute value of our f of x minus our L of x can be restricted to be below some value c. And then c is our limit of error. So now let's go ahead and just kind of do this again and see what happens. What we can do is we can go ahead and do this same concept again. So we had, once again, our format was f of x minus L of x is less than or equal to c. So let's say we want to limit our accuracy to be within, we're going to let c be 0.25. So first thing we can do is we can go ahead and say that our f of x, which was e to the x minus 1, minus our linearization, which is just x, has to be within 0.25. Well, we can go ahead, since we're taking the absolute value, we can go ahead and move some things around. First of all, we can also say that since this is an absolute value of a difference, we can also say that that we can actually switch these two values around. Because once again, we're doing absolute value. The next thing we can do is we can actually split this up into more inequalities. What I mean by that is that we can actually essentially remove this absolute value sign and say that x minus e to the x minus 1 is less than or equal to 0.25, and we also have to be greater than negative 0.25. Now what we can do is we can actually isolate our linearization to get us to where we can move our initial function to both sides of the inequality. All right, so now that we're up to here, what we can do is we can essentially solve and figure out what our error is. We can go ahead and set e to the x minus 1 minus 0.25 is equal to x. And we can also say that e to the x minus 1 plus 0.25 is also equal to x. Essentially what this means in a graphic sense is we can go ahead and shift our initial function up or down and see where that intersects with our initial linearization. So essentially, let's say we have our initial function. I'm going to go ahead and leave our initial function in orange. I'm going to go ahead and put our tangent line in red. And then we're going to look at this shift. So over here, on this side, we have e to the x minus 1 minus 0.25. So essentially what we're doing is we're shifting this down a couple steps. And over here, we have e to the x minus 1 plus 0.25. So we're just shifting it up. Now how we find our points, which are going to be our min and max, to where how far away we can go to stay within our accuracy, we look at our intersection between our tangent slash linearization line and where those points are. So, for example, right here, we can look and see that for our smaller approximation, we have 2 points of intersection. We have right here, and we have right here. If we look at our larger approximation, we can actually see that those don't intersect at all. So, I've already taken the liberty of plugging this into a calculator, since it's not a fun equation to solve without one. So essentially what we get is we get this limit being 0.199 and this limit being 1.633. So therefore we end up getting an interval of 0.199 and 1.633. And this interval will give us values that will be within our accuracy limit. So now let's move on a little bit. If we have time at the end, I may go and do another example with this, but for now, let's go ahead and move on to differentials. So differentials are kind of fun. This is actually the concept behind our linear approximation. So let's go ahead and think about when we derive a function. Let's say we have our function y equals f of x. If we want to take the derivative, we will essentially take the derivative with respect to x, we get dy over dx equals f prime of x. Well, we can go ahead and we can actually think of dy and dx both individually being rates of change. So essentially, dx changes a certain way, and then dy also changes a certain way. If we actually think of these as ratios of rates of change, we can actually go ahead and move this dx over to give us dy equals f prime of x dx. And essentially what this is meaning is that as our function changes and as x changes, that's going to yield another change in y. So essentially, y is our independent change, y is our dependent variable. Since y is our dependent variable, our change in y is dependent on the change in x. So we can actually go ahead and use this to help approximate changes in a function. So, but before we go and try an example, there's also another concept that I want to go over. We also have the geometrical idea behind this. The between our change in y and change of x. So let's say we have our graph. Let's say we just have some function like this. Well, if we take our tangent line, we know that that is the ratio between dy over dx. But let's go ahead and move forward a little bit more. Essentially what we're saying is that as x changes, y also changes. It's kind of hard to visualize with this. But let's actually go ahead and move on to like the other concept real quick. Since this is kind of hard to kind of draw out, I can go ahead and give it another shot at the end if we try. But essentially, that's kind of the idea, is that our x and y are kind of changing. There's a lot of calculus behind it. But there's another idea, is that if we have once again, if we have our function and if we have our starting point x and we move some change in x over called our delta x, we also move some delta y up. So if this is our start point and this is our end point, and that shows our difference in y. So what we're saying right here is that we can have a delta y which is equal to f of x plus delta x minus f of x. So essentially it's saying this y is our f of x, and then this is our new function as we move up. And that's essentially saying what delta y is. But that actually leads us to some interesting ideas. And so that kind of shows us another way how we can kind of approximate our change. And actually, before we move on, let me just redraw what I did earlier, make it make a little more sense real quick with our other idea. All right, so in this case, we have our function. And we have our tangent line. And this time we're starting at point x here. And we can think about this as if we move over on our tangent line, we can call this our change in x, and this is our change in y. Because this is a ratio between these, sort of like our slope, because normally we think of slope as being delta y over delta x, and this is sort of the same a very similar concept. But we have to think, but remember this one's kind of This just kind of ends up giving you sort of something similar to a tangent line. And that brings us to our next idea. Those equations and those visualizations kind of show those are very, very similar concepts. And that also shows that if we have two graphs, if we have a graph and we have our different definitions, we can actually tell that if dx, so when we did our linear approximation, we showed how that was actually a good estimation if x was close. And we can treat dx as being equal to our change in x. Now, our delta y was in relation solely to what we had on our graph of our f of x, whereas our dy is related to our tangent line. But if dx and by extension delta x are very small, then we can actually say that dy can be an approximation for delta y. And this is the same logic as linear approximation. So now let's go ahead and try some examples to kind of show this. So for our first example, we want to find dy and delta y when y is equal to x squared plus 3 cubed as x goes from 1 to 1.02. So once again, we can kind of think about this in a couple different ways, as sort of linear approximation with our dy dx, or just in general how our y values just change in terms of our delta y. But because this value is pretty small, we can go ahead but this value is pretty small, but we need to just double check and see if this would be a good approximation. Sorry if I just kind of talked in circles for a minute. But yeah. So now we already said that dy is equal to f prime of x dx. So first of all, let's go ahead and figure this out. So we have dy. If we take the derivative of our function, we can go ahead and use our chain rule. So we can pull that 3 exponent out in front times x squared plus 3, following our chain rule, times the derivative of our inner function. So the derivative of x squared plus 3 is 2x. Times our dx. Now, let's go ahead and switch colors and look at our delta y. So we already said that delta y is equal to f of x plus delta x minus f of x. Or, better yet, it's just saying f of our new minus f of our initial. And now let's just double check and see what our dx is, since we're still missing that right here. So if we're going from 1.02, from 1 to 1.02, that is going to be our change in x. So therefore, we can just take 1.02 minus 1, which is 0.02, and that is going to be our delta x, which we already established that delta x and dx are the same. So we can just go ahead over here and plug that in. So now it's just a matter of plugging our values. So over here, let's start with our dy. We get dy equals 3 times 1 cubed is 1, plus 3 times 2 times 1 is 2. I'll drop my exponent right here. There we go. Times our dx is 0.02. Over here, we just plug it straight in. We get delta y equals 1.02 squared plus 3 cubed minus 1 plus 3 cubed. So over here, let's look and see. We get 3 times 4 squared, which is 16, times 2 times 0.02. And this is going to go ahead and give us a dy of 1.92. Now let's move on to our delta y. This one, I went ahead and plugged in this part into a calculator. So 1.02 squared plus 3 cubed is going to give us 65.959 minus. This one we get 1 plus 3, which is 4 cubed, which is 64. So therefore, delta y is going to be 1.959. If we look, we can see that these are very, very similar to or very, very close. So therefore, we can actually let this be and show this is actually a pretty good approximation of what we're trying to look for. So now that we've showed that, let's try another example before we move on to min and max. So in this example, we have a sphere with a radius of 25 inches with an error that is less than that's less than or equal to 0.05 inches. What is the volume error? All right, so once again, we could really use either method. We could go ahead and we could use either our delta y method or our dy method. But once again, this 0.05 is a pretty small number, and ultimately that delta, if we tried to go ahead and solve for both, that delta y is once again going to be kind of ugly to where we have to probably plug stuff into a calculator. So I would go ahead and use the approximation. dy is approximately delta y. So we have, so now let's go ahead and look. So first of all, we're wanting to know what our volume error is. So our volume is equal to 4/3 pi r cubed. Now we need to go ahead and figure out what to do. So let's go ahead and take the differential of this. So essentially, if we derive this with respect to r, we're going to get dv over dr equals 4/3 pi r is going to be 4 pi r squared. And then we can just move this over, dr over, to give us dv equals 4 pi r squared dr. So now let's go ahead and look at our problem. They already told us that r is going to be 25, and that the change in r, or the error in r, is going to be at max 0.05. So therefore, if we're trying to find the maximum volume error, we need to go ahead and plug in our maximum radial error. So what we can do is we can plug in and get dv is equal to 4 pi times 25 squared times 0.05. All right, now let's go ahead and look at this. We have, so if we plug this in, we get 4 pi times 625 times 0.05. And if we go ahead and break this down, we get we can go ahead and get 125. All right, so now let's go ahead and double check our error. So this may seem kind of like a lot, especially in terms of volume, but let's go ahead and check and see if this is actually a good approximation. Let's go ahead and compare. So we have a potential error of 125 inches cubed, and that seems like a lot. But the thing that we need to do first is let's go ahead and compare this to our initial volume. So let's go ahead and compare to our initial volume. So our initial volume is going to be 4/3 pi times 25 cubed. If we go ahead, wait, 125 pi real quick, excuse me. All right, so now let's go ahead and see what we get here. So we get 4/3 pi times 1 times 15,625. All right, so now in order for us to kind of truly, so just looking at it, this looks like a very small, this looks very, very small in terms. But if we want to go ahead and double check real quick, let's go ahead and look at our percent error. So of course, our percent error is going to be our difference over our original. So then let's go ahead and look and see. So we get or actually a better idea is going to be what percent I'm sorry, give me just 1 second. Yes, so actually, but instead of doing our percent error, excuse me, we're going to be looking at, I misread my notes, we're going to be looking at our relative error. And our relative error is essentially just going to be what our differential is over what our actual is. So in this case, we would be getting 125 pi over 4/3 pi times 15,625. And then this would give us a relative error of 0.006. Or if we want to go ahead and turn this into percent, into a percent, it would be 0.6%. So as we can see, that's actually really a very, very small difference. All right, so now let's go ahead and move on to our min and max. So now let's go to our relative, min and max / relative extrema. So now let's go ahead and think about extrema R. So we can break down extrema into two parts. We can have min and max, our two, or what our extrema are. We can have a minimum value and a maximum value somewhere in a function. But there's also two other aspects we need to look at. We have to look at relative versus absolute. Relative is whenever we have, is just looking at values close to a point. Absolute is whenever you have values over an interval. Now, an interval can be from negative infinity to infinity, or we can go ahead and break it down into just a smaller domain, say from let's say we're just wanting to find from -10 to 10. You can still have an absolute extrema on that. So, so now let's go ahead and kind of write this out in a more mathematical sense. Essentially, we're going to go ahead and do more like actual mathematical terms. If we want to go ahead and break this down and say that we have absolute extrema over an interval C, then we can say that our absolute max is whenever we have some point f of c, as if we have x equals c, and then C and f of c is greater than or equal to the entire rest of the function on the interval. Similarly, for absolute min, we can say that we have an absolute min if it is the smallest point, so f of c is smaller or less than or equal to the rest of the function on D. Now, if we go ahead and look at our definitions for relative, we can say that we have a relative max whenever we can have a relative max whenever f of c is greater than or equal to f of x when x is close to c. Similarly, for a relative min, this occurs when f of c is less than or equal to f of x when x is near c. So if we look at this graphically, let's say we have a graph of a function and it looks something like this. And let's say we break up our interval like this. We can see that if we go ahead and look at further, that the absolute highest point of this function is going to be right here. This is going to be our absolute max. But we also have some peaks over here. We have one right here, and we have another one right here. And these are going to be a relative max. They're peaks, but they're not the highest peak. Similarly, if we look, we can see here that if we draw a line, well, actually these are pretty similar in the same spot, so we could actually say, let's see, draw a line. This one is ever so slightly lower, so this one actually is going to be an absolute min. Meanwhile, this one is going to be a relative min. All right, so now let's go ahead and move on to a couple theorems before we do an example. So first thing we need to cover is the extreme value theorem. So our extreme value theorem states that if f is continuous on the closed interval a to b, then f will have an absolute max and an absolute min. at some point C and D on the interval A to B. So essentially, this is just kind of basic logic. So this is just kind of breaks down to some basic logic. So if we have a continuous set, we have a continuous function at some point, no matter what our interval is, there will be a highest and a lowest point. Now, that is not to say that there are some situations to where we can sometimes have 2 points that are the highest or 2 points that are the lowest or both. In some cases, we can get, like in some cases, we can have a graph like this. Sort of like our sine function, to where we can have, and if this is our interval, we can see that we have, pretend these are the same height. Like we could have two that are the exact same height and 2 are the exact same depth. Those would still both be the absolute, since essentially their y values are the same. And sometimes you'll have a situation to where you'll have an interval maybe like this, where even if you're not at an actual peak, you still have a highest and a lowest point. This brings us over to Fermat's theorem. And that essentially says if f has a local, or in other words, relative, max or min, at some point C, if f prime of C exists, then f prime of C equals 0. Now, there is a very, very long proof in the book showing why this works. If you want to peruse the proof at your own leisure, feel free to, or you can go ahead and ask your prof, since they can do a much better job at explaining this than I ever could. But essentially, knowing that we have these two, so we have this theorem as well. Then then after this, we have one more definition before we can kind of combine a bunch of stuff together. The next thing we have to define are critical points. And critical points or critical numbers are going to be a number C on the domain such that f prime of C equals 0, or f prime of C does not exist. And critical points are going to be something that we're really going to carry on for a long time. So I'm going to go ahead, and since this is such a kind of a big thing, I'm actually going to do a really, really quick example. So let's say, for example, we are going to have we want to find critical points on x plus 1 over x squared minus 4. So we need to find whenever our function is equal to 0, whenever our derivative is equal to 0 or does not exist. So let's go ahead and break this down. Let's go ahead and do a quick quotient rule to where we get our smaller one, x squared minus 4, times the derivative of our top minus the derivative of our bottom times our top over x squared minus 4 squared. All right, so we get x squared minus 4 minus 2x squared minus 2x over x squared minus 4 squared. This gives us negative x squared minus 2x minus 4. All right, we can go ahead and factor out a negative 1 to give us this. All over x squared minus 4 squared. So now if we want to, so since we have a fraction, we need to go ahead and figure out where this equals to 0 or does not exist. So this derivative would not exist if our denominator equals 0. So for D and E, the denominator equal to 0, so we get x squared minus 4 squared equals 0, which gives us x squared minus 4 equals 0. We can factor this to x plus 2, x minus 2 equals 0, and then this will give us critical points at plus and minus 2. If we look at our numerator, if we try to find when x equals 0, we can do x squared plus 2x plus 4 equals 0, and this one would be doing our quadratic. Since this does not appear to be something that can easily be factored, we have to do our quadratic formula. So negative 2 plus or minus the square root of 4 minus 4 AC all over 2a. We can see right here in our quadratic formula we're left with having to find the square root of negative 12, so therefore there are no critical points when x equals 0. So therefore, our critical points are just going to be at x equals plus or minus 2. So now, after that little tangent, we're going to go ahead and combine all these theorems together. If we combine all of this together, we can now say, so as we said, critical points are going to be numbers in our domain such that f prime of c equals 0 or does not exist. And we also said earlier that if f has a local min or max at x equals c, then f prime of c will equal 0. And we also said that on a domain, we'll get back to the our extreme value theorem in just a second, but combining those two, we can say that if f has a local min or max at x equals c, c is a critical number, or also known as a critical point. So now that we know this, we can actually be able to figure out how we can go ahead and solve for our min and max. So now we can combine this as well as our extreme value theorem stating that on an interval, there's always going to be an absolute min or max to create a method to solve for our min and max. This is going to be called the closed interval method. So essentially what our closed interval method says that we need to find, first we need to find critical numbers on our domain, whatever that may be given the interval, and plug those into our initial function. That once again comes from saying that whenever we combine our critical point definition and our Fermat's theorem, saying that if f has a local min or max, then at C is a critical point. Next, we can say that using next thing we do is we go ahead and we plug in endpoints into f. This comes from our extreme value theorem. So even if let's say we have no critical numbers on our domain, we still have to have a min and a max on that interval. Somewhere we do, and it's very likely they could be at the endpoints. And even if we do have critical numbers on there, those are going to be relative ones. That doesn't necessarily mean that it's going to be absolute highest or lowest point on the graph. And then the last thing that we're going to do is we're going to go ahead and say that our absolute max is going to be the most positive value, and our absolute min is going to be our most negative value that we get pulled out. So now let's go ahead and do some examples. All right, so the first example that we're going to do is we're going to go ahead and once again we are going to find our extrema on the function 2x cubed plus 3x squared minus 12x plus 4 on the interval -4 to 2. So our first thing once again, our first step is find our critical points. So when we find our critical points, we're going to take our derivative. So derivative of 2x cubed is 6x squared. Derivative of 3x squared is going to be 6x. And the derivative of minus 12x is going to be -12. And derivative of 4 is just 0. And since the domain of this is all real numbers, what we can do is we can actually go ahead. We just know that this is going our critical numbers. We're not going to have any that aren't going to be at do not exist, but we may have some where it equals 0. The first thing we can do is set this equal to 0. We can go ahead and pull out a 6 to get us x squared plus x minus 2 equals 0. And we can get x squared plus x minus 2 equals 0. Then we can go ahead and factor this out to x plus 2 and x minus 1 equals 0. Therefore, we have critical numbers at x equals 1 and negative 2. So then our interval was from -4 to 2, and both of those do lie on our domain, so we can go ahead and check this off and check this point off. Now the next thing we have to do is plug these into our initial function. So we need to go ahead and plug in f of 1, which is going to get us 2 times 1 plus 3 times 1 minus 12 plus 4, which is equal to 2. So we get 2 plus 3 equals 5, minus 12 equals negative 7, plus 4 is going to be negative 3. We need to find our f of negative 2, so we're going to get 2 times negative 2 cubed plus 3 times negative 2 squared minus 12 times negative 2 plus 4. We can go ahead and break this up, and so we get negative 2 cubed is negative 8 times 2 is negative 16, plus we get 3 times negative 2 squared, so 3 times 4 is 12. So then we get negative 12 times negative 2, so that's going to be a plus 24 plus 4. So therefore, we're going to get negative 16 plus 12 plus 24 plus 4, which is going to give us 24. Our next step is to go ahead and plug in our endpoints into f of as well. So we are going to get f of negative 4 equals, we're going to get 2 times negative 4 cubed plus 3 times negative 4 squared minus 12 times negative 4 plus 4. So give me just 1 second, please. While you guys go ahead and work on that. All right, so right here we get 2 times negative 64 plus 3 times 16 plus 48 plus 4, which is going to break down even further into, so we get negative 128 plus 48 plus 48 plus 4. So once again, it is negative 128 plus 48 plus 48 plus 4, which is equal to negative 28. And then we get f of 2, which is equal to 2 times 2 cubed plus 3 times 2 squared minus 12 times 2 plus 4. Therefore, we get 2 times 2 cubed, which is going to be 16, plus 3 times 2 squared is going to be 12, minus 12 times 2, which is negative 24, plus 4. And that is going to give us 8. All right, so now we have everything plugged in. So now it's just a matter of looking to see what is the highest and what is the lowest. So once again, our values are -3, 24, -28, and 8. All right, so if we look at this, the most -1 is going to be at -4, -28. So that's going to be our absolute min. Then, if we once again we look again, our most positive is going to be at -2, 24. So therefore, we can say that we have an absolute max at -2, 24 and an absolute min at -4, -28. We have about 10 more minutes, so let's go ahead and try to do one more. All right, once again, we need to go ahead. Once again, we are going to find the absolute extrema on square root of 3x squared plus 4 on the interval -2, 2. All right, so once again, our first step is to go ahead and find any critical points. So let's go ahead and look and see what we have. First thing we need to do is we need to go ahead and take the derivative of our function. So we're going to initially start with d over dx of 3x squared plus 4 to 1/2. All right, if we apply our power rule first, we're going to pull out that 1/2 times our 3x squared plus 4 to the -1/2. And then lastly, we're going to go ahead and apply our chain rule. So we're going to get the derivative of 3x squared plus 4 is just going to be 6x. If we rewrite it, we're going to get 6x over 2 times the square root of 3x squared plus 4. So now we need to find our critical points, which as we stated, are going to be whenever x equals 0 or undefined. So first, let's go ahead. So first, we're going to set both the numerator and the denominator equal to 0. Since the numerator will get us when x equals 0, give us whenever our derivative is equal to 0, and the denominator will give us when it does not exist. So 6x equals 0 is going to be x equals 0. Now we have 2 times the square root of 3x squared plus 4 equals 0. We can go ahead and move over that 2 to get us the square root of 3x squared plus 4 equals 0. We can compare both sides to get us 3x squared plus 4 equals 0. Now we can go ahead and keep moving. We can get 3x squared equals -4. Divide by 3 to get us x squared equals -4/3. Now the problem is if we take the square root, we're going to get the square root of a negative, so therefore there's no we're not going to get any critical points that will yield do not exist. So our only critical point is going to be at x equals 0. All right, so now let's go ahead. So now we have to just go ahead and plug in f of 0. So if we get, so let's go ahead and plug in f of 0. So we get f of 0 equals the square root of 3 times 0 squared plus 4. 3 times 0 is going to cancel out just to get a square root of 4, which is 2. The next thing we need to do is go ahead and look at our endpoints. So what we're going to do first is we're going to go ahead and plug in each value. So we're going to get f of negative 2, which is going to be the square root of 3 times negative 2 squared plus 4. This is going to go ahead and get us 3 times 4 plus 4, which is going to be 12, which is going to get us 12 plus 4, which is the square root of 16, which is 4. Lastly, we need to go ahead and plug in our last endpoint, f of 2, which is going to be the square root of 3 times 2 squared plus 4, which is once again gets us square root of 3 times 4 plus 4, which from our last one we know equals 4. So I can go ahead and look through and see. So our smallest number is going to be 2. And we actually, since both of our endpoints give us 4, we can also say that we have two of the two bigger numbers. So therefore, we have one smaller, so we can say we have our absolute min at 0, 2. And since we have two values that give us 4, and those are both those are going to be our biggest values within the set, we can also say that we have an absolute max at negative 2, 4, and 2, 4. And that is going to give us the rest of our values. So that is all the time we have for today. I hope you guys have a wonderful day and good luck on any homework and exams.